first, let me see.
While he's setting up, could you all also make sure you're able to log on to the hotel's website, so the internet access? Because after him, we're going to go online to use the Barrett calculator. Alright, so just log on. If you all need a password, I think it's Hilton Honors or something like that. It's written down somewhere. Are you ready? Good.
Okay. So we start at 11. Okay, which formula should I use? Okay, the eye is a two-lens system. Alright, it has the cornea, and in cataract, you remove the cataract, you put in an IOL. So it is a two-lens system, it is a virgin system. You need to take account into the two-lens system. Cornea contributes about 2/3 of the refractive power of the eye, and the IOL or post-operatively, or actually the lens is about 1/3, because the IOL you will factor in whatever you need to correct the refractive error as well. Today we have different kind of formula. We have regression. Regression by and large has disappeared because they are not accurate. These are based on large data. You use statistical fit and you try to generate a formula out of it. Of course, these are no good. Despite the SRK, I think using 30/1000 eye is still not good enough. Then the second generations are the theoretical. The subsequent generation, these are using physics equation, but they are mainly thin lens. Thin lens means assume that the lens, whether the cornea or the IOL, has no thickness, has no anterior curvature or posterior curvature. It is just one plane. Of course, in real life, thickness and curvature, whether front is more curved or back is more curved, will affect the principal plane of the IOL or the cornea as well. So the more modern theoretical formula actually is becoming thick lens. And there are some others, like for example, the modern one, they are either iterations or artificial intelligence, which is different from regression. I've shown this is the sources of error. From here you can see the first one, which is the post-operative anterior chamber depth. What does that mean? That is the function of our formula. Because you can never predict, you will never be accurately know where is the IOL going to be post-operatively. That will have to be determined post-operatively. You can only try to predict where the IOL positions will be, and that's the function of formula. If this is the major source of error, it means formula is the major source of error, and that different formula becomes critical. Alright, this is with ultrasound as well as optical, as shown you earlier on. Short eyes and long eye, you can see that the short eye is even more likely, more at risk of having refractive surprise or wrong power, because everything, the contribution of everything else becomes very critical as opposed to longer eye. So from thin lens, we have moved to thick lens. Like I said, from regression, we have moved to equation, moved to iteration. The last two is because of computational power. Today computers are so powerful, iterations means you keep running the equation, running the computer until you find what you think is the best fit for the eye, while artificial intelligence is based on huge data but using modern AI algorithm to predict. The last two have been very good and formulas are coming up. So what I'm going to show you are data, my own data, comparing the different formulas so that you can make the judgment yourself. This is the syllabus. Unfortunately, in the limits of time, we can only talk about some of these eyes and not these eyes. So what I'm going to talk about will probably be first the free range eyes. I will emphasize a little bit more on the extreme IOL. If you have time, of course, we can go to the extreme IOL, the extreme eyes, but I don't think we have that much time. We can touch on IOL concerns, which I think is a major misunderstanding. And if we still have time, we'll touch a bit on the toric as well. Okay, this is the free range eyes. This is eyes of one IOL power, so that we don't get the different IOL to contaminate the data. There are almost 400 eyes. There are one set from 5 diopters to 30 over diopters, but that will, even though that are not necessarily extreme, but will give us an idea of the extreme power. Now these are the different formulas involved from SRK to these two are my own formula published in 2008. They are not that great anymore. And then some of the newer formulas like EVO, RBF, and Barrett. What I want you to look at is the spread of the IOL in these almost 400 eyes, the prediction error. That means the post-op actual refraction minus the predicted refraction, that is the error. Alright, if the post-op refraction is exactly as predicted, there's zero error. Alright, but all of them will have some error because IOL power comes in half a diopter stack. You cannot expect not to have errors at all. And refraction is by no means perfect. So this is the extreme end on the negative side. Negative means post-op the patient is actually more myopic than the predicted refraction. On the plus side, it means post-op refraction is more hyperopic than the predicted refraction. More on the plus side. Right side plus, left side minus. This is the first quartile, 25%. This is the second quartile. The second quartile is also the median. I mean, on average, almost on average, all right? This is not a normal distribution. So that's why we use median quartile instead. This is the third quartile. And of course, this is the fourth quartile. What we are interested in is, of course, the median, as well as the interquartile, the spread of the third and the second and the first. That will give us an idea of how badly spread the IOL is. Of course, the first quartile spread and the last quartile, there's much more variable, but these are probably approaching outliers. So if the formula is good, the median should be, all these are optimized. The median should be as close as zero as possible, with the box, the two boxes, as tight, as small, as compact as possible. That is an indication of good formula. Alright, of all this, you can say that the RBF is very good. And these are older RBF. All these new formula like RBF, Barrett, and EVO, they keep changing every few months online. Alright, so this is very good. This EVO is very good. Barrett is very good. You can see some of the more conventional formulas we are familiar with. We are familiar with, such as SRK, Holiday, Hoffer-Q, even Haggis. They are not as good. Look at the interquartile. These are the third against first. You can say that this is 0.44, 0.46. Haggis is approaching half the diopters. The conventional formula is more than half the diopters. EVO is 0.42. SRK2 is almost 1 diopter. That is a terrible formula. Then we look at the median absolute error. Median absolute error means the prediction error, the actual refraction minus the predicted refraction. Alright, so it's a prediction error, but we disregard the sign. So whether it's hyperopic prediction error or myopic prediction error, we treat them as the same. This is more to look at the spread of the error. Again, this is zero quartile, first quartile, second quartile, third quartile, and the outliers as well. And what we are interested in is the median absolute error, which by right, if it's within a quarter of the diopters, is good. If it's small, it is not as good. The more compact the box, the better. Alright, so the median absolute error, the RBF, Barrett, Evo is less than a quarter of the diopters. The rest are higher than a quarter of the diopters. SRK2 is almost half a diopters. This is the second indicator of IOL formula performance. Finally, the percentage of eye predictions, again, how many percent within how many diopters for the different formulas. This is a quarter diopters, how many percent within the quarter? This is half, this is 3/4, this is 1. In the old days, we used 1 diopters to predict, to compare. I think 1 diopters is too far-fetched now, and it's probably better to use half a diopters now. The formula is getting very good. So here you can say RBF, Evo, Barrett more than 80%. Highgate is approaching 80%. Highgate is using U-Lip constant. Highgate T is using triple optimized. Offer, SRKT, holidays, they are not that good at all. Alright, they are still reasonable, but not good. And SRK2 is terrible. And then we look at the excellent, alright, without going to extreme eye, because this population have some very long eyes, almost not extreme yet, and very short eyes. If we look at SRK2, there's a gradient, which means for short eyes, it is on the positive side. For long eyes, it is on the negative side. That's a trend. Same with SRKT. Alright, there's a trend for short eyes. It is more likely to be myopic. For long eyes, it's more likely to be hyperopic pulsar. These are errors. Holiday 1, alpha Q is worse. SRKT is not so bad. That's why they say SRKT is actually use SRKT for longer eyes. That's the fast teaching. Alright, Higgins is relatively alright, whether triple or U, there's no particular trend. Barrett seems to have a little bit trend, but not too bad. Evo and RBF has no trend. That is a sign of good formula. First, the error should not be big. Secondly, the error should not have trend. So once you have trend, this, and this should not be used for long eyeball and short eyeball. That's what it means. How about chromatometry? The same data set. You can see there's a trend, there's a trend, there's a trend. Evo has no trend, there's a trend, and small. This is not so much of a trend for the day 1. Alpha Q, not so much of a trend, it's up, down, up, down. Highgate now has a terrible trend with chromatometry. I mean, the steep cornea, the flat cornea, steep more than 46, flat less than 42, should not use Highgate at all. RBF and Barrett and Evo have no particular trend with K and relatively small. So if you want to use, if you have extreme K or extreme axial length, from here you can see that you should use either RBF, Barrett, or Evo. The rest of the formula has trend, especially in the extreme of eye. Alright? What about target refraction? That means you don't aim for 0. It's monovision, you may aim for -2. For example, so from minus to positive territory, SRK2 has trend again, dependent if you're on a minus, if you aim patient to be -3, for example, you're most likely end up patient -1, not -3. That gives you a hyperopic error. Alright? If you want to aim plus, I don't think anybody will want to aim the patient to have plus unless the other eyes is done 20 years ago and highly hyperopic, for example. Alright, this has a bit of trend, SRKT has strength, Holiday 1 has strength, Alpha Q has strength. Alright, that means if you don't want to target emmetropia, that means you don't want to target more than -1, all this has error. The only RBF also have a bit of error, Barrett, RBF, but you can see it's up, down, so it is not too bad. Evo, all on the same side, there's no particular trend. These are just spurious, all right? You can't read a trend into it. So if you want to target a patient ametropia, then the conventional formula has failed again. So after all is said and done, the most important thing, even if you still want to use SRKT, Hoffotil, Holiday 1, for example, well, at least don't use SRK2 anymore. Alright? So this will go back to overview again. I'm going to talk a little bit on IOL constant because I think this is seldom talked about, but I think it's very important. Well, IOL formulas, like I said, is a two-lens system. The IOL constant, or ELP, effective lens position, which is an optical function, or you can use LHP, lens haptic plane, which is an anatomical function. They are slightly different because it depends on the thickness of the lens. Alright, but for these purposes, we may assume them the same. The longer the axial line, the longer the more posterior the ELP, as shown here. Alright, different axial length, the position of the lens is more posterior for long axial length and more anterior for short axial length. That we know. What about K? The steeper the K, the more posterior, the steeper the K, the more posterior, the flatter the K, the more steep K. This is the standard K. This is steep, more posterior, flat K, more anterior. But of course, it also depends on the white to white. Alright? And the ACD, of course, if you measure the ACD, the longer the ACD, the lens is likely to be more posterior. That part we know. And of course, the design of the lens, even same platform, different design. For example, some the steeper anterior or steeper posterior curvature, they will change the A constant. For example, these two lenses, there are three pairs. One is anterior asymmetric biconvex, the other one is posterior biconvex. You can see the A constant can be very different. Alright, so is this a function of the IOL too? Of course, anterior chamber IOL being right in front is usually 0.3 or 3 less than posterior. Right, this is a single piece, two single piece, aspheric biconvex, anterior asymmetric biconvex. You can see again the A constant is different. So it's a function of the optical design as well. So then a lot of questions are asked is why the same IOL for ultrasound, for optical biometers, you have two different constants. Well, I want to highlight it to you. This is ultrasound. This is the same eye. First, with ultrasound using a keratometer, for example, is 43.81 now. The axial length measured by ultrasound is 23.44 millimeter. If this IOL have an A constant of 118, for simplicity, alright, for simplicity, we use SRK2, but I say don't use SRK2, but just for illustration purposes. Because most formula in SRK2 is linear, it's easy to see the relationship, okay, but please don't use it. So to predict for emetropia, this eye will need 19.96 diopter. With IOL master, you measure the same eye. The K is 44.04, it's the same eye, but it's a different keratometer. The outcome is different. The axial length now is 23.54 millimeter. This is 23.44 millimeter. I'm not going to say which is more accurate. I'm just telling you here for IOL constant. If you use 118.4, so 118.0 for ametropia, it will need 19.42 diopters. Alright? Now, two same eye, different set of instrument, predict different IOL power. Are you to say that if I put these two different IOL power, I will have the same refractive outcome? That's not likely to happen because the IOL power is the same, the eye is the same. So if I want to put in 20 diopters, ultrasound said I would have minus 0.03 diopters residue. For IOL master, I have minus 0.41 diopters, half a diopter versus perfectly ametropic. That cannot be. So to harmonize these two, you play with A constant, IOL constant, and that is a function of IOL constant. So if I want to use IOL master now, the same IOL, if I change the A constant to 118.4, then the predicted ametropic power for this eye now is 19.91 diopter. It is closer than this now. Alright? And the residual now is minus 0.07 diopters. Alright? And that is why A constant is different when you use ultrasound and when you use optical biometer. And optical biometer, even the different optical biometer, there is slight difference. Fortunately, the difference is not a lot. But if you want to be exact, if you go into ULIP, of course ULIP hasn't updated for the last, since 2016, you'll find that AL scan from NIDAC optical biometer has its own set of constant, Lenstar has its own set, IOL master has its own set. Fortunately, they are quite close, but the same cannot be said about ultrasound. Now, this is my own eye. I don't have cataract yet because I'm an easy subject, no data protection required, no need consent. I just go through all the optical biometers that I have in my department. Alright, if I use any patients, I will have a lot of paperwork to do. Different optical biometer, the K is different. This is ultrasound using different keratometer is different. Not too bad. The axial length, 26.63 all the way to 26.45. Calculate using 119.3, if I use the IOL constant 119.3, and if I want to have cataract surgery, the predicted ametropic power now you can see from 10.3 diopters to 11.3 diopters, using the same constant, using this variety of biometers. So the expected refraction therefore can be very different from no to half a diopters. By the way, you know I'm a bit myopic. That's why my eyeball length is a bit long. So if I were to put in a 10.5, assume that I have this outcome. This is assuming spherical equivalent 0. Alright, so what is this is now I said I want this to be my expected refraction. Now I have post-op data. I have spherical equivalent 0. I want the system to predict, whatever measurement to predict that I have this expected refraction, calculated refraction, working backward, the A constant, and readjust the A constant. Alright? And therefore you can see the different set of instruments, there are whole lots of different constants. Alright? With ultrasound is terrible. Alright? Now, with a few optical biometers, you can see the measurement is very close to 1 and 9. Alright, that's why I say the A constant for Landstar and IOL master won't be that much different. There is different, but won't be that much. The difference is in K, but the K is also quite similar. Alright, but if you look at IOL master and Landstar, the K is a little bit different, but nonetheless, it is 119.2 to 119.3 A constant. So it's only 0.1 different. It's not going to make a big dent in your IOL power calculation. If you look at ultrasound now, same model. Alright. We have 3 ultrasounds in the clinic. They go through, you can see they measure very differently. Okay? Of course, if you use different curvatometer, it's going to be even more different. What does this mean? It means that ultrasound is not as precise. You measure one same model, one machine to another machine is not necessarily even close. 2, you measure today with the same ultrasound and you measure again tomorrow, they will still be slightly different. But not the case with IOL or optical biometer. If you measure today, if you measure in Bangkok using optical biometer, you go to Singapore, you measure, it's probably very close. And because it's very close, you can pull off the data worldwide and work backward, and you have the unit constant. But ultrasound is so variable, you can't pull world data together, and that is why you don't have the unit constant for ultrasound. You can't, because it is so variable. The same eye measure, even with the same machine, can be so variable, but not the case with optical. And here we show you that A constant can never be the same once you change instrument. So, if you measure with IOL master, and you have a pentacam, and you use a pentacam K and fit it in, be very careful, because the constant is not the same anymore. Alright? It may not be big, but it's not the same. If you take a big data set, you're going to be disappointed. Okay? So, this is just a repeat. So, this I hope brings to you, 1, why the A constant is different. 2, why there's ULIP and there's no ULIP for ultrasound. Okay, so I will summarize. I don't think we have much more time. So first about the evolution of formula with ultrasound. In the past we have earlier formula, we don't see them anymore. Subsequently we have this 4 formula, which is very popular. And with optical biometers, we still use this formula because we don't have any post-op data, we don't have big enough post-op data to find out how good this formula is. But like I said, optical formulas measure far more precise than ultrasound. We can make good use of the data. So Hygis was the first formula optimized for optical biometer. Subsequently, there are newer formula come along. And with the greater precision with optical biometry, I think it is time to move on to this new formula. How about ultrasound? Can we use this formula? Well, not so much Hygis, because like I said, constant. For the other few formula, you really have to readjust the constant a little bit. They are not the same. Alright. Today, most of the constant on the box are based on optical. 10 years ago, they give you one based on ultrasound, one based on optical. Today, it's mainly optical. So if you use ultrasound with today constant on the box, if you optical constant, you may have to make some readjustment. Okay, so just to summarize, all this formula depends on the actual length, depends on the K for standard axial length 22 to 25, 26, most formulas are fine. Hofferteville has traditionally said better for short eye. They are pretty good for steep and flat cornea, not so much variable, but it's not good for long eye at all. SRKT Holiday One are slightly better for longer eye, but that's about it. But if you want to have everything else, it is either Olsen, RBF, or Barrett. Olsen is difficult to use. RBF, Barrett, and Evo is available online. You can go online. If you're optical biometer, you can assume to use the same constant. If you're ultrasound, you have to be a bit more careful. So with that, thank you very much.
Thanks very much, Han Bo. Any questions for Dr. Pham while I get set up? So Dr. Pham's taught us all about the sort of science and the numbers behind the calculator. So I'm just going to say a few quick words from the practical point of view, and then let's go online and use the Barrett calculator, which I think globally now is probably the most popular formula. Now the Barrett suite of calculators can be found on the apacrs.org website. It's free of charge, and this is the formula I use every day. Now, when you go to the APACRS website, you will go to the drop-down menu here, and this is the Barrett suite of calculators. Han Bo has talked a little bit about the universal calculator, which is used just for a spherical lens, okay? And I will say straight away that I don't use this very much anymore. I always start today, by almost every case gets a toric calculator, and for the post-refractive eyes, I would use this, and this is really used pretty infrequently. Now, just a quick word about why the Barrett Universal 2 works better than SRKT. Those of you who are still using, I hope that this convinces you. Now, we know from many, many papers that have been shown that the Barrett formula has the lowest prediction error for many things when you compare the different formulas up here. So that's why we use it. The traps in biometry, Han Bo alluded to that. Very long eyes, very short eyes, unusual K values, post-refractive eyes. Those are all minefields for us. And you've got so many formulas. Now, SRKT is widely used, but you can get problems with very myopic eyes, which is very common in our Asian population. SRK2 should no longer be used. Now, why is that an issue? That's an issue because IOLs change shape as you're using them in more and more myopic eyes. The change is that the IOL changes from convex to meniscus shape, and the math is different, and that's why you get refractive surprises in highly myopic eyes. Let's look at this example. This is a patient who's very myopic, 29 millimeters long eye, and if you use the SRKT, as was done in this particular case, SRKT, it would recommend an Alcon lens plus 0.5 for -2 outcome, plus 0.5 in the Alcon case, and for an AR40 that. But what happens if we do this with the Barrett Universal 2? You can see that the Universal 2 recommended a 1.5, 1 diopter difference for the AR40, and for the Alcon 60 is also a 1.5. So it's a 1 diopter difference. SRKT 0.5, Barrett Universal 2 1.5 diopters. Why is that? This OCT image of the lens in the eye shows you the biconvex thicker lenses, and when you go to the low dioptric power, you can see that the IOL shape has changed to a meniscus. The Barrett Universal 2 factors this in and protects you. You don't have to change formula, you don't have to get other things. This will give you the much more accurate outcome. So the Barrett formulas, Universal 2's unique selling proposition is that you really only need to use this one formula for all your biometry. You don't need to really think too much, and it's available on all biometers, and as I said, it's free. And this protects So now, having said that, for the sphere, I would say that today, many of us in this room, say Dr. Chi, Dr. Pham, we implant 80% of our patients get a toric IOL. Far more than a spherical IOL or a non-toric IOL. So I always start by using a toric calculation. If I were to ask all of you up there, when do you do a toric calculation? At what level of K value do you do a toric calculation? What would you say? And you? More than one diopter. That's a very common answer, and I will tell you after today's talk, I hope you will throw that statement away. But you should do a toric calculation in every patient. Right? So let's go online now. For those of you, please go open up your browser. So I'm going to take you through the APACRS website. So if you go to www.apacrs.org at the top and enter, this is the screen that you're going to come up with. Okay, I'm just going to refresh this page. Go down to IOL formula. You can see the drop-down menu that I showed you. So those of you who want to do this with me, please do so. You're going to select the Barrett toric calculator. Oh, sorry. So if you open up the www.apacrs website, go to the IOL formula, see the drop-down menu, select Barrett toric calculator, and then you've got to go down to the bottom of the page, say that you read and accept the disclaimer, accept, and then you're going to open up this page. Oops. This is the page that I see every day in my clinic. At the end of my clinic, I open this up to do all my toric calculations. So when you go in here, say we're going to do a left eye in this case. Now on this right here, you see these two boxes saying optional K1, K2. That's what Dr. Pham mentioned just now. Some people like to take K values from other instruments and put it in. Don't do that, okay? Because use all your data from your primary biometer, whether it's LensStar or IOL Master, use your own one. Unless you're very advanced, you want to key in your own case. So don't use that box. Choose the left eye, say, and then key in your other data. Put in your name, put in the patient's name. Now the next thing, very important, is your personal constant. If you go to that personal constant box you see on the right, when you hit that button, a drop-down list of all the toric lenses that have been optimized for the Barrett calculator is there. Now, assuming that you use, say, we like to use the SN6ATX, which is the Alcon toric IOL as the most stable toric IOL, you can see once you select that, the A constant is optimized and put out here, and the lens factor. Then let's key in the flat K and the steep K. So let's say this is 42 at 90, 42.5 at 180. This is only half a diopter of astigmatism, right? Just now somebody was saying 1 diopter before you start doing toric calculation. So for this, you probably wouldn't have done a toric calculation. But this is what I'm hoping to change. I'm going to show you what the result is. Axial length, let's say at 24. ACE, let's say it's 4. Target refraction gain for 0. In the left eye, we'll key in the SIA. Now for those of you who are using incisions 2.4 or less, key in an SIA of 0.1. That's been shown mathematically to be the most accurate, and you don't put in 0.5, that's way too high. So 0.1 for an SIA if it's less than 2.4. Incision location is the left eye, so it's 0. Lens thickness, we'll say it's 4. White to white, lens thickness, we'll say it's 4. White to white, we say it's 12. Now, okay, so we've got all the data input, and this is all the data I get from my IOL Master. So if you're IOL Master, put this in. If you're LensStar, you put in that whole set. Now, the most important button at this stage is the Calculate button. The Calculate button is what calculates your stuff for you. So you see that when I press Calculate, it will now populate that chart down there. Okay, that chart down there, you can see that the data that I've inputted is inputted into the formula now. It tells us we've got 0.82 against the rule astigmatism. So it's no longer 0.5, it's 0.82. Now this is using one set of K data, and if I want to get the results now, I can just click on Toric IOL. And this gives me that the result here, I should put a 22 diopter SN6AT2 to give an outcome. But you all know that we now use several different biometers, and you're going to be much more accurate if you use different sets of K data. So if we go back to patient data here, we're going to press calculate again. Remember, always press calculate when you go here, and then go to the K calculator. What is the K calculator? Can you remember that button up there? It's very important. I press K calculator, it opens up this page, which allows you to input 3 sets of K data. So the first set I want to put in, if you select your biometer, which was the IOL Master in this case, you key in 42 at 90, 42.5 at 180. That's the first set of data I put in on the previous page, if you remember. Okay. Now I use 3 sets of Ks. My second set of Ks is typically from an autokeratometer. And let's say for this, say it's 42.3, and say it's at 100. And let's put this at say 43 at 10. Now you've also got to click this box here called select to include. The computer needs to know that you want to use this data. And this is useful later on if you want to just compare say 2 sets of keratometer, you can deselect this box. Now the third machine I use is typically a Pentacam, but you could use manual K, you could use any of the other machines if you want to, and let's call this a 41.75 and let's make this 110, even further out, okay? And then let's move this down. That back in, but you can just carry on practicing that while I just enter this data again. Calculate is the first thing. You've got to select I here. So left. So you press calculate. It populates the I with the next images in there. Then we go to K calculator. That's the one for you to input the 3 sets of data. IOL Master. 42 at 90. 42.5 at 180. See, I've input 3 sets of K data and selected to include all of them. What's the magic button we press? Calculate. Yeah, remember calculate? And when you press calculate, you see that this box here on the right here will fill up. So anyway, if you press that button as I showed you there, it would have brought you to the new measurement of the integrated K. Let's just try it one more time because that's important. I don't know what happened to that. There was a problem with that, obviously. Did anybody manage to get, have you all managed to input the 3 sets of K data?
Yes.
Okay then, can you press the calculate button and you should see that box on the top right fill in. Okay, then what you do is press patient data. Top left, patient data. It brings you back to the first page. Okay, from there you press calculate again. When you press the calculate again, it's brought that integrated K together with the axial length together. And now you press a toric IOL at the top. You see that button, toric IOL? And that has now given you a number. What has it told you to use now?
22.500.
And you'll see at the bottom, sorry?
It's 22.0 at 7 degrees.
Okay. And you will see at the bottom, it gives you the name of the 3 instruments you applied. That tells you you used 3 sets of K data to get a triple optimized K that you use for your toric calculation. And you see, it asks you to use a T2 or a T3. T2 to get the lowest residual astigmatism.
T3.
T3. So what's the point I'm making? You see, at the beginning I showed you 42, 42.5. Many of you would not even have done a toric calculation. But it's telling you not to even use a T2. It's telling you to use a T3 because this is against the rule astigmatism. As you all know, it's got half a diopter hidden against the rule, plus half a diopter that's on the front surface. That's why you're needing a T3. So if you learn nothing else from this talk, go home and use the toric calculator in every case on the Barrett because it factors in posterior cornea, and you'll find you get very much more accurate results. Any questions from anyone here about using the calculator? What I suggest you do, because again here it's difficult, maybe over lunch or during tea or tonight you'll play with the calculator, see whether you can get on with it or not, and if you have a problem with it, then tomorrow during the wet labs, and we can do some of this in the other room with those who are not doing the wet lab, and we can go over the use of this calculator again. But so that's using the Barrett toric calculator, which I hope is helpful to all of you. I'm sorry, there was a glitch here on the website. I couldn't get my calculator going, but you guys got it. So I'll just end there, and I'll ask Dr. Panet now to come up and give us his next talk. They're talking to us on difficult cataracts. Thank you. Thank you very much.
What?